series of papers between 1998 and 2002. We fix our phenomenon algebra as the observable algebra of our physical system for now, and consider the category of all unitary abelian phenomenon subalgebras. And this is a very simple kind of category. It's simply a concept. You can have an abelian subalgebra, and you have some smaller abelian subalgebras lying in there, and so the simple thing is that we only have morphisms, we have at most one morphisms between two objects in this category. And these morphisms are denoted by iota v prime v, where v prime is contained in simply all the inclusions. So we call this the context category, and it's denoted by v of r. Okay. Then the next thing you want to do is to define a certain pre-sheaf, and if you know that it's okay, if you don't know that it's also no problem, I think. You simply take the Gelfand spectrum for each of these abelian subalgebras. We take the Gelfand spectrum, and these are the objects in this pre-sheaf, which itself is a category, of course. And then we have to say how to get from the spectrum of a larger algebra to that of a smaller. This is also as simple as you could wish for. You simply restrict the elements. And the elements in the Gelfand spectrum are pure states. Explicitly, we would think of them as pure states. They're also multiplicative states. Okay, and you see the morphisms in the context category are going from v prime to v, so from the small algebra to the larger, while these restriction mappings go from the Gelfand spectrum of the larger algebra to that of the smaller. This is exactly what we need to have a pre-sheaf, namely a pre-sheaf which we call sigma here. This special pre-sheaf is sigma. Is a contravariant functor. This is the contravariance is exactly this going in the other direction. It's a contravariant functor from the context category to set, and this is what is called a pre-sheaf. And just for notation, if I simply write sigma, I mean, well, the collection of all these Gelfand spectra with these restriction mappings, and they are contained in this category, which is set v of r. This is to be read all the functors from the opposite category of v of r to set. And the opposite category of the category simply is you take all the objects you have in the original category and you reverse all the morphisms. And this is exactly what we do here. The original morphisms go from v prime to v, and here they go back from what is the set belonging to v, which is sigma v2. So there's nothing deep here. Just for those of you who may not know this stuff. And what we suggest, and what becomes clearer now, is that the spectral pre-sheaf sigma may serve as a kind of quantum analog of phase space, and I want to make this a little clearer. Well, first of all, what Eichmann and Butterfield did is this reformulation of the Kornspectrum theorem. Namely, one can ask if we can pick from each of these many Gelfand spectra one element such that they fit together under this condition. If I have a subalgebra of some other algebra, then I would have the element I pick down here given by that I pick up here and then restrict it down. And doing this is called a global section of the pre-Schiefer category theory. And now Eichmann Butterfield showed, and my paper was generalized to all phenomenon algebras, that having such a global section would mean having a valuation function. This condition exactly means what you do in different contexts must fit together in the right way. And then you see you would have an evaluation function. This cannot work. So we know we can have no global section for this pre-sheaf. This is the reformulation of the Kornspectrum theorem. Okay, now we want to get some intuition what this means. Global sections as points, this is the headline. And what has this to do with points? Well, global section, now if it existed, yes, it would be a morphism from a certain object in the category set V of R up to sigma. I call this the one element presheaf. For those of you who know, this is the terminal object in the presheaf category, and this is simply the presheaf consisting of the singleton set at each of these algebras, and of course the morphisms, the restrictions are just the identity. Well, if you look at the analog thing in set, it's very simple. The terminal object there is the one element set, and if I have some other set S, then a morphism from this one element set to S, what does it? It picks just one element of S. So the points of S are just these morphisms, 1 to S. And the fact that we have no global section thus means that we have no points in this little more abstract sense. We do have terminal object 1 in the category we're now working in, which is this presheaf category, but we have no morphisms going to sleep. And this is, well, it's not too bad. This is just what you would expect. The Kortlandt-Speckle theorem can be read in the way that there is no phase space in the way we have in classical theory. Of course, I promised to show what we still can do and why this still could be regarded as some kind of generalized phase space or replacement of phase space. And so I was a little scared about the statement down here. Somebody will take offense, but now quantum logic has been bashed so thoroughly that I have no fear to do it again. Okay. Well, this was in Bob's talk, so I can do this very shortly. What we ordinarily do and have in quantum logic is simply the lattice of closed subspaces of Hilbert space, and then they suggested in 36 that this would be the logical structure for quantum theory. And at first sight, this looks similar to what we have in classical propositional calculus, where the Hilbert space now takes the role of phase space analog, and in this subspace, in the closed subspaces, correspond to the propositions. And the point is that we do have severe interpretation problems. As soon as we have at least the two-dimensional Hilbert space, we get a non-restrictive lattice. And probably most of you will know this, the quantum breakfast is a nice example for that. If you go to a quantum hotel and then order breakfast and they offer you eggs and bacon or ham, you do not get eggs and bacon or eggs and ham. This is simply not true in a non-restrictive lattice. It can be seen very easily. This is nothing, as I said, it happens in dimension 2, and if we look at a two-dimensional Hilbert space, and it can be real in Hilbert space, and we are in the plane basically, and if you look at subspace, and there simply will be lines with the origin, and of course, so let's take 3 different lines here, or whatever. E, H, and well, B or H is the subspace spanned by those, it's the whole plane. E and this is E. While here, E and B is the intersection of these subspaces, just the origin, just like E and H, it's all the origin. So on the right side, you only get the origin, which obviously is different from E. And this is really a big problem. We cannot interpret this in any good sense. So it's fair to say that it's not really useful for doing physics, and also the generalization of that are not. Nonetheless, what we want to keep is